some usage of conservation laws in case of the equations shown here. Well, first of them is well-known KdV equation, and the second is well-known KdV Burger's equation. And in the end, I will speak about generalized Cartwright-Lewis Burger's equation, which has non-constant coefficients by members concerning dispersion and viscosity or dissipation. I'll start with KdV. Well, everybody knows what KdV is, and I just use this slide to state the notations and some terminology. The most prominent solutions of KdV are solitons. They are compact, they are traveling wave solutions, and this is I think that I will spoke about how do they behave, and this behavior will be described with conservation laws. There are infinite many conservation laws for KdV, and 4 of them are listed here. They have usual names as mass, momentum, energy. The 4th one probably has no name and is not well advertised. The second slide shows which are the constant which are conserved for the soliton. The soliton is described by 2 parameters. One is A, which has a relation with the amplitude and velocity, and the second one is S, which is shift. Since the conserved quantities are constant, they are shown here. They depend only on the first parameter, the A. It is easy to see that after first 4 conservation laws, which are calculated here, there are infinite number of other one. K indexed K is the specific constant, which is for the mass is 12, for the momentum is 48, and so on. They have no some interesting meaning because it's just norming and nothing more. But they will use it in for the formulas. This is something which everybody knows. I made this slide only to show that for this very form of KdV, B Hamiltonian structures are generated by these operators. It is well known that any bounded data and with compact support asymptotically becomes a sum of solitons plus a reflected radiation wave. That is a radiation wave. It will be shown on numerous videos and graphs below. But it is theoretically, it is known how what is the construction of this asymptotic form. To obtain it, you have to have A's and shifts. In this formula, it is P's. These A's are a discrete spectra of the differential operator shown here, and P's are calculated with this formula. Of course, the answer is theoretically known, but given arbitrary initial data, it is hard to obtain this A's, especially in a case when it is done, this data is made not in analytical form. So some estimation for the for this asymptotic made solely with the conserved quantities may be very useful. Here are shown two kinds of data that leads to splitting of initial data, this initial data, into solitons. The red one splits into 5 solitons, and the blue one splits in 4 solitons, and this may be very easily indeed predicted. This is splitting into 4 solitons. Once again. I'd like to especially show the form of the reflected wave. It is a number of packets of quasi-harmonic oscillations. And then this is 5 splitting. And once again. Well, how to predict this, this result? Let's proceed and see. First, we look at the reflectionless splitting. It is the case when there is no reflected radiation wave. After some deliberation, in this case, the initial data splits into a number of disconnected solitons, which has different speeds. And therefore, any conservation law this one or this one, is in fact integrals over each soliton separately as well. And then we have this number of results for first four for the first four conservation laws. Q is initial data, and its mass will conserve and be split into n summons, and so on. Thus, we obtained a system on parameters A, which is quite simple, and the right parts of these equations are easily calculated. Mass and momentum and so on is easily calculated even for non-analytical data. But it's rather hard to expect that there will be no tail. The tail means that the equation for conservation of initial data has one more summand. Every equation has one more summand. This is conservation for the reflected wave. And therefore, we have discrepancies instead of 0 in the left part, in the left-hand side of the equation, as it was in the case of reflectionless splitting. We have now these discrepancies, and they are also constant. After some deliberation, they became constant. After the splitting is over, some constants, which is hard to obtain, of course. But they are nevertheless of some use, because these discrepancies or conserved quantities for the reflected wave are alternating in sign. Moreover, I have some ideas why it is so for the first four conservation laws. I have also a hypothesis that it is true for all quantities, but I have no proof for that so far. Sorry. It's understandable, because if initial data is positive, then since the motion is ruled by the transport equation, all this mass of initial data moves to the left. So, reflected wave moves to the right. So that the mass, at least of initial data moves to the left, and therefore we see that this inequality holds. Even more simple is the sign of momentum, because momentum is integral over u square, and therefore it's natural. To see why the fourth discrepancy is negative, I'd like to show once again how is made the reflected wave. It is almost harmonic, or packets of harmonic oscillation. Therefore, this is small because for every positive hump, there is negative hump. And this one is not small because it is also almost harmonic, but negative. This is, of course, not the proof, but at least plausible argument. And it can be applied to the fourth conservation law after it is reduced to equivalent form. I'd rather not to speak in any length about this because I have no strict proofs. But in all probability, this is true. If we, remove discrepancies from the general case equations, these discrepancies, then instead of equation, we obtain a number of inequalities. This one. Recall that the left parts, the left-hand sides of these inequalities are easily obtainable. You should not come to spectral analysis of some obscure data to obtain these integrals. Let's see the simplest case when there are only two solitons resulting after splitting. And then we have a very short number of inequalities, namely this one, this, and this. Notations are given to the right. P by K is some normalization of conserved quantities. Then we have to obtain some point A1, A2 in a space of parameters, which can be found only between two curves. In this situation, there is no solution to the problem of two solitons splitting. And here you can obtain some points inside this segment. The negative answer means simply that you can not expect that splitting will result in 2 solitons. But the number of solitons may be easily obtained. After all, these two inequalities must be satisfied, and they will be satisfied for some n. And this will be shown here. Of course, it's very simple, and let us see how it works for the two splitting soliton. Why this cubic curve does not intersect this line? That is why this two inequalities has no common points. It will change if we take to obtain admissible domain, the point A must be over the point B. Here is the case, and here is not the case. It is simply to get the coordinates and of these points, and for the given values of P1 and P2, we get one or other graph. The main idea, very simply, indeed, is to make the number of solitons more, to increase the number of solitons. Then, if we take n solitons, then the point B will have n coordinates all identical. And for the point A, also identical coordinates can be calculated. So if we want A be over A to be over the B, we have to acquire such inequality, which leads in this example to the inequality shown here, and there will be, for appropriate n, there will be a situation when the admissible domain is non-empty. For arbitrary P1 and P2, this equation, this inequality is as simple as that. One more remark. There are points of intersection of these curves. And the points of intersection means that both inequalities, this and this one, becomes equalities. And this means that the points of intersection is the parameters of non-reflection splitting. In these points of intersection, for these parameters, for this P1 and P2, we will obtain two soliton splitting and no reflected wave. There was two videos. Let us see them it once again.
Я говорю, приятного аппетита.
When this process of splitting is over, you can easily measure the amplitudes of these peaks or these solitons. Since peaks are the amplitudes are intimately connected to the conservation laws, these conservation laws, conserved quantities may be easily calculated, and they are given in this slide. As you have seen, the number of solitons after splitting is 5, and let us use the formula. This formula. We see that P is normalized values of conserved quantities. They may be calculated independently, and we receive the right answer. Once again, mass of the excuse me, I will show you once again the initial distribution. Here is the initial distribution or initial data for the KdV. To measure its mass, momentum, and so on, you can use very simple integrals or even numerical methods and obtain conserved quantities for this initial data, and then substituted in this formula and obtain the number of resulting splitting solitons. Sorry. This formula this formula is quite simple, and admissible domain is usually not very great. Therefore, we can easily evaluate the parameters A's in the resulting solitons. Well, I'll proceed to another part of my talk. In fact, I will speak about a very special case of KdV-De Vries-Burgers equation, which is given by the first line here. It is a full differentiation of this form. This equation has a form of conservation law. Therefore, the mass is conserved for solutions of this equation. But the momentum does not. Here we can see the rate of decay of the momentum, and it is a simple formula. You can see that momentum is maybe increasing or decreasing with respect to the sign of derivative. The examples which is given below are of a special function f of x. It is numerically constant outside a finite neighborhood of origin. That is for at plus infinity, it becomes a Korteweg-De Vries, and at minus infinity, this is also Korteweg-De Vries, but with different coefficient by the dispersion summand. The model, which is numerically and analytically analyzed below, consists of soliton, which starts, well, I recall that solitons for positive coefficients in the equation, the solitons moves to the left. We take a soliton far in the right and let it move to the left. It comes to a region of instability of coefficient f, and what becomes of this soliton? By the ideology that everything that comes to them as initial data for KdV, it is clear that after transgressing this region, we will have maybe a number of solitons and maybe a reflected tail also. Let us see what it is in some examples. Suppose that transient that passed through the region soliton is well solely sole soliton, one peak, and then we have since we have one real conservation law, then conservation of mass is here, and what is given by this equality, and momentum or impulse evolution corresponds to the sign of f, derivative of f. So the equality is was true, and we must choose the inequality in this, the sign of inequality in these inequalities with respect to the sign of f3. By the way, reflection coefficient, sorry, and I write reflection, it's refraction coefficient. Refraction coefficient is a ratio of velocities, and velocities are proportional to, well, where are this the velocities are proportional to a square. So therefore, the refraction coefficient is given in the is such as given in the last line. Now look at the case when after initial soliton taken at the right moves through the region of non-constant dispersion and dissipation, and comes to the constant dissipation to the left as a pair of solitons or bisoliton. As well as in the first argument, there may be, and there usually are, reflected waves. This system of equations and inequalities may be written in a simple form if use notations given in the first line. Then it will come to this very simple, indeed, system. This also may be illustrated by a simple graph. The straight line is the equation, and other curves are thought great inequalities for different parameters k. Recall that k is a ratio of coefficients by the dispersion term. If k is small, then the admissible domain is a domain between this low curve and the straight line. It's there is no new restrictions on on A, and in this case, in fact, only one soliton is the resulting is in the resulting splitting process, appears in the resulting splitting process. In this, for K greater than the line, there is the admissible domain is also between the straight line and this curve, and no new restrictions also appear, and therefore the result also will be one soliton in the left, and for small variance of in this case, the admissible domains consist of two, well, triangles, almost triangles. This one and this one. In this case, two bisoliton appears. Well, let's see some examples. The upper curve is the function f, here denoted as phi, and the dot line, dashed line is derivative. Therefore, I remind that soliton moves in this direction. It moves from the region where dispersion is great to the region where it is smaller. Let's see the process. The reflected wave is almost non-existent, but nevertheless you can see it. This is B-soliton case. This is similar, but similar example, but the coefficient in the left part is very, very small. It corresponds to the case when the cubic curve is on the whole lower than the straight line. And there must be, for that matter, only one result, only one peak, only no splitting, but diminishing, enlarging of soliton. Let's see how it works. My computer doesn't see any reflected wave. I don't know whether it is really true or it is as small as it cannot be seen. It is also B-soliton result, and I'd like to show since there is no reflection, then this corresponds to this intersection point. When there is no reflected wave, then inequality becomes equation, and then the result may be here. In fact, if you measure the peaks on the screen, you will get somewhere. You will get points somewhere near this intersection point. somewhere there. So in fact, the reflected wave exists, but is so small that in this resolution can be seen. This is the case when which we are discussing. And the last example, it's some numbers which cannot be commented in this form of speaking. The last example is when instead of decreasing the coefficient by the dispersion is increasing. This is coefficient by dispersion, and this is coefficient by the viscosity summand. This case corresponds to this domain when k is great enough so that cubic curve is over the line, the straight line. And here is how transforms the soliton meeting this non-homogeneous region. It is one soliton solution and decreasing one, so that some energy has been lost. Now, thank you for your attention.
Thank you. Let us thank the speaker. Anyone has questions? Well, if we have no questions, let us thank the speaker. Yes, we have. Yeah, you may ask.
Hello, Alexey. Thank you for your presentation. Yeah. Do you know the paper by Cartman with one of his colleagues who did something similar using the conservation laws to calculate the amplitude of solitons?
I know a number of works, articles dealing with this problem, that tries to describe the evolution of initial data as recent as recent year. I knew, but it somehow differs because, if as you can note that my approach is very simple indeed, and they think about more details, while I think mostly about the number of solitons, very rough estimation.
Probably it will be useful to you to refer to the book by Cartman, Nonlinear Waves in Dispersive Media. I believe you know this book, which was published in Russian and then translated into English, and you can find similar results of this book.
Okay, thank you for your advice.
Thank you.
It will be very nice of you to give me a reference, send me a reference if it's not very hard.
Any more questions? Do we have?
Okay, maybe I have a question. Sorry. You basically use only two first conservation laws in your analysis, right?
Yes.
And have you tried to consider any further conservation laws? Do they have any change in your analysis, or perhaps can improve it somehow?
Yes, surely. I spoke at length about admissible domain and use to describe it only two conservation laws. If I use more conservation laws, then I will get more strict restrictions, and the positioning of solution will be found much more exactly. In fact, if I know all conservation laws, I know the solution exactly as is the property of integrable equation. But the usage of higher conservation laws makes this procedure not very nice, easy. Yeah, my main goal was to show that using only two conservation laws, I can obtain the number of solitons and obtain some estimation on their velocity and amplitude and so on. Of course, if I use more conservation, I will get much more exact results. That's sure.
Thank you. Thank you.
Any more questions? Well, if we have no questions, let us thank the speaker again. I believe this is it. Thank you. Thank you, everybody.